Welcome back to campus and welcome to Stochastic Computing. My name is Dr. Holmuth and I will be your instructor for the next 15 weeks. Some administrative bits, reading, and this will be very important throughout the course of the semester. By the 3rd of September, which is a week from Thursday, I'd like you to have the following reading done. It's not a lot, but you'll still need to invest the time in this reading. In the Barron text, our main text for the class, Chapter 1, Sections 1.1 to 1.2, which are pages 1 through 4, and then also in the Barron text, Chapter 2, Sections 2.1 to 2.2.1, pages 9 through 14. It will be really important to make sure you're keeping up with the reading. Make sure you are spending the time, an hour a day at least, on this course. Do something every single day, not just when something is due. First homework number 1 is out. It's a bit of a discrete math exercise, as well as to get you acquainted with Matlab. It is due a week from Tuesday, September 1st, a week from today, when you look at this. At 11:59 and 59 seconds, so that's 1 second before midnight on September 1st. You have a week to do it. It's ample time in which to complete it. Please make sure you download and start it right away. Do not wait until a day or two before it's due to start the homework. That is a recipe for failure. Make sure you follow the instructions. It is electronic format only. Okay, so what is stochastic computing? It's the study of systems that are non-deterministic. For many types of systems, you can have multiple different outcomes, but each time you run the system or observe the system, the outcome can be different. So suppose you're standing at the proverbial fork in the road, and you see maybe cars go this way and cars go that way. You observe over one period of time, maybe it's 5 seconds, you see a bunch of cars go this way. And the next instant, you observe cars, and maybe 2 cars go that way. And then maybe at another instant, you see 1 car go this way and 2 cars go that way. And it's not the same every single time. In stochastic computing, we deal with systems like this, and the tools we'll use to deal with these systems will be the tools from probability. So let's take a look at Target. This is the Target here in Dover. And suppose you were looking through a camera, observing all the customers that come into Target throughout the course of the day. Now, certainly, that's doable. In fact, stores like Target do that now. And they have automated systems that count the number of customers coming through the door at any given time. Now, of course, the reason why you want to do this is because you actually have actual data, and it'll tell you so many customers came in, say, on a Saturday evening during the hours of maybe 6 p.m. to 9 p.m. Fewer customers came in on a Wednesday morning from 6 a.m. to 8 a.m. And you might use data from such a system instrumenting the customers that arrive in time at Target to decide how many employees you should have, how many cashiers you should have open, and so forth. Another example, let's look at a pedestrian walkway. Now, of course, the traffic lights, they turn red, and when they turn red, the pedestrian signal comes on. Now, if you had information counting the number of pedestrians, and this person's jaywalking here, going not on the crosswalk, but nonetheless, if you have a system that counts the number of pedestrians at any given period during the day that might go across the crosswalk, you could certainly set the crosswalk light appropriately and the red and traffic lights appropriately to accommodate the pedestrians that might need to walk across. So during non-busy times, you make the lights longer. During more busy times, you make the lights a little bit shorter, right? So less time for pedestrians, more time for motorists. During low traffic days, low traffic meaning pedestrian traffic, and then maybe more time for pedestrians during the high traffic periods of the day, and less time for pedestrians during the low pedestrian traffic periods of the day. And how would you do this? You'd instrument this with a camera and literally build a system that's going to count all of the numbers of people that go across the pedestrian crosswalk for given periods of time during the day, all throughout the day and during the week. So here's an interesting example using stochasticity and non-determinism to make decisions. And that's really the interesting part that we're going to study towards the end of this semester. The name of the game for this course is how to make decisions in the face of uncertainty. And a really important application of that deals with autonomous vehicles. So let me play this video.
For a vehicle to drive itself, it needs to know where it is in the world, and it also needs to know what's around it. Based on these factors, it needs to be able to make smart and safe driving decisions in the real world. And once you get in the car, you start to get a real feel for the way the technology works and what it's like in real driving situations. So there are a few things that have to happen before the car can safely drive itself. First, it has to figure out its location in the world. So we use GPS, but GPS isn't always that accurate, which is why we rely on our other sensors like the laser, which picks up on details in the environment that help us identify a more precise location. So think of the sensors as the car's eyes and ears, but with eyes that can see far off into the distance and 360 degrees around the car. And the great thing about having all these sensors is that they can talk to each other and get cross-checked information about the environment. So while we take in a ton of information using our sensors, it's our software that really processes all of this and differentiates between objects. All these objects are visible on the laptop that the safety drivers use while testing the vehicles. Based on what the vehicle senses and processes, these objects will be represented by different colored boxes. Cyclists will be red, pedestrians yellow, and the vehicles will appear as either green or pink. These boxes demonstrate the processing that takes place within the software. And think about the complexity here. People look different, cars have different shapes and sizes, yet despite these nuances, the software needs to classify these objects appropriately based on factors like their shape, movement pattern, or location. For example, if there's a cyclist in the bike lane, the vehicle understands that this is a cyclist, not another object like a car or a pedestrian, so the cyclist appears as a red box on the safety driver's laptop. And the software can also detect the sense of hand signal and yield to them appropriately. When our engineers think about where the car should drive and how, safety is always the top priority. So the vehicle takes into account many things like how close it is to other objects or matching speed with traffic or anticipating other cars heading in. For example, as a passenger, it can feel a little uncomfortable passing by a large vehicle on the road. Our engineers have taught the software to detect the large vehicles, and the laptop shows them as larger boxes on the screen. As our vehicle passes by a large truck, it will actually keep to the farther side of the lane and give ourselves a little bit more space. We've also taught the vehicle to recognize and navigate through construction zones. The vehicle sensors can spot the orange signs and cones early to alert the car of any lane blockage ahead, and then we can change lanes safely. Another thing that's really important is for the vehicle to drive in a naturalistic way, because when it's natural and the car abides by social norms on the road, it's also safer. For example, at four-way stops, people typically rely on eye contact to communicate whose turn it is. And in our case, the vehicle inches forward into the intersection to indicate its intent. So my role as a safety driver is first and foremost to keep the car, myself, and everyone around me safe. And in addition to keeping the car safe, I also provide detailed feedback to developers and let them know the car does anything that maybe I wouldn't have done personally. Maybe the car wasn't assertive enough in a lane change or wasn't fast enough at a green light. We provide the detailed feedback so they can fine-tune the whole driving experience. By getting out there and driving in the real world, we're getting a better understanding of what exactly it's going to take to improve the safety and comfort and ease of transportation. And that's really what our project's all about.
Okay, so as you can imagine, the other obstacles and how they move is non-deterministic. You can't determine it the same way. It doesn't happen the same way every single time. And so you need the tools of probability to help the car make decisions under uncertainty. You come to the same four-way intersection, even the same time of day, every day, and the other obstacles around you are going to behave differently. So this is an example of decision-making under uncertainty. Okay, so how do you describe what you saw? Well, you saw different obstacles. You saw bicycles. How do things move? Well, that cyclist made a turn, did a hand signal. How do you make decisions about things like how you move? Well, if you see pedestrians crossing when you make a turn, you have to stop for those pedestrians because they're in a crosswalk. If you see a cyclist change lanes in front of you and do a hand signal, well, you have to slow down a little bit, put more distance between you. How do you make decisions about where you go? Now, certainly you saw that example where you had the construction site. Now, the map would dictate, well, you're supposed to be able to drive in 2 lanes, but what your sensors tell you is that you can't go in 2 lanes. You have to make a lane change in order to get around the construction cones because there's construction on the roadway. And so all of this needs the tools of probability, and all of this requires you to ultimately make a decision based on information that you measure. So let's take a look at the course outline and how we're going to do this. So most of you are academic juniors. Who's a junior, right? Most of you. And so now, congratulations, you're finished with the introductory material, methods, and tools. So up to this point, you've been studying data structures and programming languages and things like that sort. You've just kind of been accumulating the basic tools you need, and now, your junior year, you're being introduced to the actual discipline of computer science or information technology. Now, in this course, what we'll do is introduce methods, approaches, and tools for ultimately making decisions about something you see, phenomena, or a system involving uncertainty. And so this has a reliance heavily on reading a mathematical text, and maybe for some of you, it's not something you have a lot of experience with. We'll certainly cover some examples and go over some tips about how to do that. But most importantly, over the course of the semester, we'll learn how to build systems that will help you make decisions under uncertainty. And so how we're going to do this? Well, the main texts are twofold. Probability and Statistics for Computer Scientists, and make sure you get the 3rd edition by Michael Barron. And we'll be covering material from the first 7 chapters. We'll be looking at aspects of probability. We'll look at how you identify sources of stochasticity or non-determinism. We'll look at ways of modeling scenarios. We'll look at how you describe uncertainty. We will implement prototypes and introduce you to decision-making under uncertainty using simulations. And the tool for implementing these models will be Matlab. Matlab is a mathematical modeling tool, and the good news is it is at no cost to you. We have the Matlab site license, and there's the URL for the site license. This is limited only to students in the division. You have to use your DSU email address in order to take advantage of this. It's going to require you to sign up, register for an account on mathworks.com. There's the contact information, the link. So please install Matlab ASAP because Homework 1 has a Matlab assignment. So our tool for implementing models is going to be Matlab. And Matlab is nice because it allows you to focus on mathematical modeling and not the computer language. It has extensive domain-specific function libraries, and these are called, in Matlab speak, they're called toolboxes. And Matlab is a very popular engineering tool used throughout industry for all sorts of things, from financial forecasting to automotive design, aeronautics, robotics, you name it, Matlab can do it. In fact, I encourage you to download as many toolboxes as interest you, even beyond what is required for this course. You have access to full-blown Matlab, all the toolboxes that MathWorks makes, and Matlab has some award-winning tutorials and online instruction. I encourage you to take advantage of that. Okay, there are other useful resources, certainly YouTube. You can look up all sorts of video shorts on concepts in probability. There are other textbooks available online for free. And certainly there's our library, and it's going to be a little bit harder to use the library if you're not in person, but there's lots and lots of freely available information on the web to help you. Khan Academy is quite good. YouTube has dozens and hundreds of different really high-quality pieces of material. And here are some links to free statistics and probability books. Okay, so assessment. There will be 4 project assignments, collectively worth 25%, 4 written homework assignments, collectively worth 25%, 2 written exams, collectively worth 25%. There will be a research project towards the end requiring you to submit a report and also to code a prototype. You will be presenting your research project. The research project will be your final exam, and then class participation is 5%. It is a fixed grading scale, and these are the scale for the grading. A is 90 to 100%, B is 80 to 89%, C is 70 to 79, D is 60 to 69, and F is 0 to 59%. What topics will we be covering? Well, first, introduction to uncertainty and events and randomness. We'll look at probability and random variables. We'll look at discrete random variables and their distributions. We'll look at continuous random variables and the distributions. We'll consider the Bayesian approach for how you introduce new evidence in a probabilistic model. We'll look at simulation and Monte Carlo methods. We'll also talk about stochastic processes and look at applications. So, the course time. Lecture begins promptly at 12 noon. Simple policy, arrive at class before lecture begins. Be on time or don't attend at all. Respecting your time, I will end lecture on time. I also plan and estimate a specific amount of time for each module. Work, I do not accept late work. It will not be accepted. I know sometimes life gets in the way. I ask you to communicate. Plan your time accordingly. Poor planning is no excuse for being late. I understand things like jury duty, family situations, health issues. Please communicate. You can always contact me by direct Slack message, not the group message on the Slack channel for the course, but direct Slack message or a direct email if it is something of a personal nature. Make sure you communicate. But late assignments will not be accepted. Please make sure you get homework done right away. Every year, I have a group of people who lose a lot of points because they failed to take the deadline seriously. I invest a lot of responsibility in you, and I treat you like professionals and the adults that you are. With privilege comes responsibility. Manage your time accordingly. Do not submit the assignments with a minute left before the deadline. Invariably, something always goes wrong. Make sure you give yourself enough time to comfortably submit your assignments. Okay, make sure you follow instructions. How to succeed in this class. Engagement is the name of the game. Use the discussion forum, not on Blackboard, that should say Slack. Ask questions. This course is a total of 198 pages of material. That's just over 13 pages a week or less than 2 pages a day. It's not very much when you talk about it as a marathon. Do a little bit of work, an hour a day, every single day. Don't wait until something is due before you start the material. It is a recipe for failure. Spend time every day, run a marathon and not a sprint. I don't need you to be Superman, staying up all night and burning the midnight oil. Be Clark Kent and just do your everyday job. Engagement with the material is the key to success. That means viewing the material, but also writing the material. Get a pencil and paper and actually work out examples yourself. That's how you do well in this class. Okay, policies. Mute your microphone if you're not participating in the discussion. Minimize the outside distractions. Be here on time. Because we're doing this online, it's going to be really, really important, and I expect the same from you I would in an in-person meeting in this online format. Be here on time. If you need to schedule office hours outside of the posted blocks of time, make sure you email me, right? And I have a procedure for that. I will propose a time. You select one. You say, yes, Dr. Holness, I will choose this time. Otherwise, my assumption is that you have not chosen a time. Late work is not accepted, so plan your time. Your programs must run and compile. I am not product support. I will not fix your programs. Any programming assignment or programming project that does not run and compile receives a 0 without review. Do not have side conversations or use your phone to text message and all sorts of other things, playing games while you're attending this course online. If you have other things that you prioritize, then please leave the class and go do that. That's your prerogative. You are an adult. It's hugely distracting, and you take away from everyone else. And collectively, your colleagues in the class have paid a lot of money to be here, so don't cheat them out of their education. Don't have those side conversations. Make sure you mute your microphone and pay attention. Choose a time and a venue and a place, a location where you can be successful that are conducive to your undivided attention in engaging with this material. And don't cheat. It's obvious when you copy things from other people or off the web. It's very, very obvious. I do check. I have tools, and I use those tools to check every single assignment. I don't enjoy it, and you won't enjoy it. Every year, there are issues concerning at least one person. So make sure your work is your own, that you can produce your answers. Okay, so what is stochastic computing? Well, dealing with uncertainty. It deals with the measurement of uncertainty, how you quantify or describe uncertainty, and ultimately making decisions under uncertainty. But the question persists. What exactly is uncertainty? What is it? Let's think about this for a moment. Well, a condition where the results, the outcomes, the near future, or the remote future are not completely determined. They can't be predetermined without error. Okay, well, what does this mean? Let me give you some examples. Suppose I flip a coin. I flip a coin. There are two sides, heads and tails. I flip the coin once. Okay, it comes out heads. Does that mean that I'll get a heads every single time I flip it? Absolutely not. I flip it again, it comes out heads again. Oh, wait a minute. Does that mean it's still going to be heads the next time I flip it? No, absolutely not. So I can't determine every time I try that experiment to try to measure or observe the outcome of a coin flip, I can't determine in the future exactly, precisely what it's going to be. So I need some tools to help me here. I roll a die. When I roll a die, I have 6 sides to the die, and I can roll a 1, 2, 3, 4, 5, or 6. Okay, it's not the same each time, especially if I try to roll it the same way each time. Picking a lottery number. Can you pick the winning lottery number every time you pick one? No. It's very, very low chance event. There are hundreds of millions of combinations of lottery numbers, and you only win if you just happen to pick the one that's drawn for a particular day. Is it the same number every day? Absolutely not. Let's say you go to the supermarket, you're at an open air market. The price of apples, is it the same every single week of the year? No, absolutely not. It changes. How does it change? When does it get bigger? When does it get smaller? How do you describe that? Let's say you're at Target and you want to observe how many customers walk into the store at various times of the day. Is that the same every day? No. The same day each period of the week, let's say every Monday morning from 6 a.m. to 9 a.m., it's not the same. How do you deal with that? What about the temperature? Is the temperature the same all day? No, it certainly fluctuates. Who will win a game? When we do have sports, well, we do have sports now. Let's say there's a football game or a soccer game or a baseball game or a basketball game. Who's going to win the game? Even for the same two teams with the same group of players, it's not the same outcome each time. What about the price of a security or stock, right? Apple stock, it goes up, it goes down. Is it the same every day? Absolutely not. So these are examples of uncertainty. But we still, in dealing with these, we still need to make decisions in spite of this uncertainty. So let's take an example of that target. And this is a coffee shop example. And this is a system that's actually a real system that has an overhead camera and is watching the so-called entry box of a retail establishment. And here we see this green square, and it's basically counting all of the people that go from the outside of the store to the inside of the store, and likewise who go from the inside of the store to the outside of the store. Now, it's not tracking identities, it's just looking at the presence. And if you notice here, there's a counter in the upper right-hand corner that counts the number of people who enter and the number of people who leave. The difference between those two are the number of people that are in the store at any given moment. So we'll watch here, these two women, it'll increase 79, 80, 81, 82, 83, and now we'll increment the leave 10, 26, 27, those who enter. And so what can you do with this? Well, if you track this over time, you can use it to determine how much staffing you need. Maybe you have an organization where the staffing level for employees working there is dependent on the number of people that are in the store, right? So this is a real example, and if you can mimic or model this computationally, now you can run your simulation and use that to determine things like how much money you think you're going to make. Because with these computerized registers, you can tell for each period of time how much money you're taking in. So you take the money you take in and you divide it by the number of people in the store for that period of time, and now you have revenue per customer, and you can use that to determine how many employees you can afford to pay, how many employees you should have on staff, and so forth. And so uncertainty exists in everyday life. And the types of things you might use in a retail establishment are measurements like how many customers visit the shop and when do those customers visit the shop. How much coffee beans should I buy next week? Well, the amount of coffee beans you buy is dependent on the number of customers and the amount of coffee that you sell. How many employees should work each shift? Well, that's dependent on the number of customers because you don't want to have the customers wait too long, but it's also dependent on the amount of money that you earn or the amount of money you bring in. How long will the drive-through line get? You don't want people waiting too long in the drive-through, right? So you want to know how many cars are coming for each period of time during the day. How many food items will I sell next week? Well, you have a register that records the food items you're selling, and you know how many customers are coming in, and that will help you to decide how much you should spend and how much of these food items you should actually purchase in anticipation of those customers. And so you still need to make decisions in spite of this uncertainty, and that's the topic of the course this semester, stochastic computing. So you have to measure and deal with uncertainty and randomness. And how to do this is the subject of this course. Now, what do you use to do this? Well, we'll need a few tools. We need tools of probability, and probability informs us on how to measure, how to describe, and how to quantify uncertainty. We'll need some theories and algorithms, and this informs us on how to model or mimic phenomena that involve uncertainty, because not only do we need to describe it, we need to mimic or model it. Then we'll look at prototypes and simulation, how we use this uncertainty ultimately to make decisions. So you're going to run these models, it's going to give you data, and then you're going to use the data to make decisions. And then lastly, inference, how to make so-called optimal decisions under uncertainty. Now, of course, we'll touch upon this only a little bit in this class, but next semester in data analytics, the primary topic of data analytics is how to make optimal decisions under uncertainty. Okay, so we will have homework 1 is already out on the blackboard. It's essentially a discrete math skills assessment, and we'll have a Matlab warm-up with that. It's out. It's due in 1 week, due on September 1st. Ooh, that's a typo. September 1st, yes, September 1st, 2020, in 1 week at 11:59 and 59 seconds. Please make sure you start that right now. Okay, so with that, we'll end there, and I will see you next time. So there's the reading once again. Please stay healthy, stay safe, and I will see you on Thursday.